The last type of process for expansion and compression of gases is called adiabatic. And you might notice that the naming here has changed a little bit. We've dropped that iso as a word part, iso meaning same. And so in this one, pressure, volume, and temperature, those can all change. Now the amount of gas and the ideal gas constant, those will remain constant. But in this case, then we can say PV equals nRT. The ones that stay constant are fairly limited here. It's just N and R. So we can rewrite this as PV over T has to be a constant, but any one of those values can change. Now what makes adiabatic processes a little different from some of the other ones we've talked about is in the other ones, if we had a situation where, say, the gas in here was really cool and the surroundings were warmer, then we could have this net flow of heat inward. We use a Q for heat. We could have a net flow of heat this direction. And if we had the opposite case where we had a really warm gas inside here and then the surroundings were really cool, or were cooler anyway, then we could have this net flow of heat outward. Okay, so that's the other processes. But in adiabatic processes, either we have a well-insulated system of our gas, or the process just happens too quickly for any heat transfer to occur. So no transfer of heat in this one. So the only change in energy that's going to happen for this gas and for the surroundings is done by work, by the force and the distance moved by this piston. So adiabatic then just means that the change in heat is equal to 0, or no heat flow. Okay, so let's think about adiabatic expansion and compression then. So in compression, our volume is going to decrease. And let's see, in this case we see volume times pressure divided by the temperature. That has to be some constant value. So we know that pressure is going to increase here. When volume decreases, pressure will tend to increase. So we have a smaller space for these particles to bounce around in, and so there's going to be more frequent collisions with the walls of the container, which means more pressure. And then the temperature is going to increase because as this piston comes down, it collides with these air molecules and it knocks them around. It makes them move faster. It does work on them to make them move faster. So the temperature will also increase. Now, when the temperature increases, these little particles that are inside here, they start moving faster. And so they collide even more frequently with the walls of the container and with this piston than they would have before, and they hit it more forcefully. That means that our pressure increases even more than it would have. So pressure increases, well, lots, we'll say, a nice precise term. So our volume decreases, our temperature increases, and our pressure increases more than either of these changes by themselves could explain. They both contribute to an increase in pressure. If we look at expansion, our volume is going to increase. And when that volume increases, when our piston goes from here to a position like this, we have more space for those particles to bounce around in, so there's fewer collisions with the walls of the container, so the pressure is going to decrease. And our temperature is also going to decrease here. So as this piston recedes, the molecules that are making contact with it, that are bouncing off of it, we can think of them as hitting this object that has some give to it. And so because of that give, they come off going at a little bit slower speed. So you might think about like playing ping pong. If somebody were to hit a ping pong ball towards you and it were to hit your paddle and your paddle was just at rest, then that ping pong ball would come off at some speed, going back the way it came. If that hits your ping pong paddle while you move your ping pong paddle backward just slightly, you have a little bit of a give to it, then you can cause that ping pong ball to move back at a slower speed. If you have enough give to it, you could actually stop that ping pong ball completely. So the ping pong ball isn't moving as fast. The air particles or the gas particles, they're not moving as fast. That corresponds with a decrease in temperature. And then keep in mind that when temperature decreases, that also means that the particles are moving more slowly, and so they collide less frequently with the walls of the container, including this piston. And when they do collide, it's less forceful. So pressure decreases, again, lots. More than it would as a result of either the volume increasing or the temperature decreasing all by itself. So we see a larger change in this pressure for a given change of either of these types than we would in the other expansion processes, or compression processes. So we typically look at we're going to spend a lot of time looking at those PV diagrams. And if we said temperature was constant, then we could have that 1 over volume, that pressure equals some constant divided by volume relationship. So we'd see something like this, or maybe something like this, or something like this, depending on what that constant value was. But for the adiabatic processes, this pressure, it changes more rapidly, and so we might see something like this, or something like this, or like this, or like this. Okay, so the red ones are more adiabatic. We have a little bit more rapid pressure change than we do in the other cases. So a little steeper slope for that more vertical section on the adiabatic processes. It's worth noting, by the way, that these adiabatic processes, because they occur for things that happen rapidly, and a lot of expansions and compressions of gases that we're familiar with happen very rapidly, there are a lot of examples of adiabatic expansions and compressions. So when you're using like a bicycle pump to pump air into your tires, you can think of that as an adiabatic compression of the gas. The motion of the pistons inside an engine, a diesel engine in particular, are adiabatic processes, and it's that process that causes this very rapid increase in temperature, which ignites the diesel fuel and continues the motion of the car, the motion of the engine, and therefore the motion of the car. So there really are a lot of things that we can do with the adiabatic processes. So our next step is going to be kind of coming back and working with these PV diagrams some more, and then just putting it all together. So what's going on in terms of work, in terms of energy, in terms of heat and temperature and pressure and volume, and all these different variables that we've looked at are going to be combined in our next few steps.